Hi, my name is Manish Gupta, and in this video, I'm going to talk about MusicGen, which is basically a model for controllable music generation. Let's get started. Why is music generation challenging? And by the way, when I talk about music generation, I mean this problem, conditional music generation. So I have some text in mind, and the user basically gives that text and expects a music piece which is conforming to this text. For example, a text could be 90s rock song with a guitar riff. And then you expect that there will be some music that will be generated, which looks like a 90s rock song with a guitar riff. Okay. Generating music is, of course, challenging. One, music typically means long range sequences, and then generating them using transformers is challenging, right? Second, unlike speech, music actually requires high fidelity, and therefore it requires the use of full frequency spectrum. So compared to normal speech, which just requires, let's say, 16 kilohertz sampling rates, music actually takes about 44.1 or 48 kilohertz kind of sampling rates, right? Third, music also contains harmonies and melodies from different instruments, which create complex structures, pretty complicated music structures. And human listeners are highly sensitive to disharmony. So therefore, it is super important to be able to somehow generate these complex structures, keeping the harmony and melody in place. Fourth, music generation sort of requires the model to have the ability to control the generation process in a diverse set of methods. For example, what is the key? What particular instruments need to be played? What is what kind of melody? What kind of genre, and so on. So therefore, music generation in general is a challenging problem, more challenging than just speech generation. And when it comes to generating music, the one of the first things is how to encode audio in general, right? Um, and then basically when you have text at test time, then how do you essentially ensure that you can actually generate music in a conditional way given the text caption? Okay, so first let me talk about how is audio encoded. Typically, audio is encoded, first of all, using EnCodec, which is essentially a convolution autoencoder. So it's basically an autoencoder. You basically feed in the audio waveform as input, and you expect to reconstruct this audio waveform at the output. This latent space is basically the space that the encodec actually comes up with. So it's a convolutional autoencoder. So there are several layers of convolution here, 5 or 6 layers of convolution here, um, which reduces the input waveform into a latent space, quantized using something called as residual vector quantization, which I'll talk about soon. Okay, so but it basically gives you that. And there is a adversarial reconstruction loss. So in one of the previous videos, which I recorded, I basically talked about this adversarial reconstruction loss, where all that looks like autoencoder, but the way you train this is basically using a discriminator and a generator, a GAN kind of loss, where you have various loss functions to control for the fidelity of the generated output. You want to ensure that the reconstruction looks as close to original audio as possible in the time domain, the frequency domain, and so on. While the discriminator, well, there are a bunch of discriminators which try to discriminate between the real audio and the generated audio. Okay. So that's that. So you have this encodec, which basically tries to take these waveforms and give you, some discrete audio units, and you take those audio units and you try to quantize them using residual vector quantization. So the reference audio may be of sampling rate fs and of length the duration d, and then the encodec actually encodes it with a frame rate of fr, which is much less than fs. So that's how it basically tries to compress the audio in some ways. Now, this representation, of course, it's not quantized to begin with. It's basically just discrete audio representation coming from encodec. Now, the next step to do is to basically quantize it. And typically, so in this particular paper, they chose to do quantization with k equal to 4 codebooks. So where there are n different possible levels in this quantization. So n is 2048, n is 2048, and they sort of try to ensure that every time point is basically quantized into 4 different numbers, such that each number could be belonging to one of those 2048 different codes. Okay. So that's that. Now, so the quantization is actually done using residual vector quantization, which basically means that each quantizer is trying to, so the first quantizer tries to basically map the whatever is the number to 2048 different possible codes, right, depending on the range. Now, what is the residual? The second quantizer tries to tries to sort of represent or encode that error. And the third one tries to make up for the error done by a combination of the error from the previous two. And the fourth one basically tries to cover for the previous three and so on. So it basically means in residual vector quantization, these quantizations done by the next few codes is basically dependent on the previous few for the same time point as well, right? So that's that. Now, after the quantization, essentially we have k parallel discrete tokens, token sequences, each of length t, and the length t of the quantized stuff is basically given by the length of this of the latent vector here, which is basically d into fr, the reduced rate r, fr, and d being the overall audio duration. Okay? So now that you have basically t time points or the t different sequences, length t sequences, each of where t is basically d into fr, and you have like k equal to 4 different sequences. Now, how do you sort of try to um, represent them as sequence steps, right? So that is what is called as codebook interleaving pattern, which is basically shown here. So you could basically interleave them in 4 different possible ways. So for example, it's a flattening pattern, and this is sort of obvious, for every time point, d into fr being the total number of time points, for every time point, what you would do is basically have 4 different codes. So well, you'll use 4 different sequence steps so as to represent them. So you have like 4 different rows here because there are four quantized values, 4 codebooks, right? And then you represent them one after the other in the sequence, right? So this, of course, basically means that your overall sequence size is going to be 4 times t because you have, for each time step, you have like 4 sequence steps in that senses, right? A more efficient pattern is basically a parallel pattern. And in parallel pattern, basically you have the total number of sequence steps is basically exactly is exactly t because you represent all the 4 codes at the same time step. Right? And then there are 2 other patterns, volley pattern and the delay pattern. So in volley pattern, the idea is you basically compute t1 to tn or the first code first for all the n time steps. And then in parallel, you basically try to represent the next few codes. Okay. So remember in RVQ, in residual vector quantization, the first code is the most important. Others are actually trying to just encode the residuals, which were not cared for by the first one. So therefore, the largest values are typically for the first one, right? So therefore, it sort of gives very high importance to the first few, first code for each of those time steps, and then the later codes are essentially encoded in parallel. Okay. And then there is also this delay pattern where essentially you have the first time point, the first code, second time point, you have, there's a delay. So essentially T1 sort of still is represented using 4 different time steps, 4 different sequence steps. However, it's not like T2 actually starts after T1 finishes. So therefore, overall sequence steps here are also, approximately S equal to T or more clearly T plus 3. But the point is that, well, that's also another way of encoding things. So surely, flattering pattern is probably a good one, but then it basically has like 4 times t, so it's not very efficient. However, if you look at delay pattern, well, it's pretty efficient because it has the overall sequence size the same as the overall time points in the quantized representation of the audio. Yeah. So now, how does MusicGen use all of this, right? What is the architecture of MusicGen? So architecture of MusicGen consists of 5 important parts that I'll talk about in this slide, right? The first one is you have the codebook, sure. So you have an audio, and essentially, you basically have sort of encoded it using your autoencoder, and then you have also done quantization on top of it. Now, which basically means that you have t different time, s different sequence steps, and at every sequence step you basically have like 4 sized vector. Now, many of them could be zero, some of them may or may not be present, right? So essentially, for example, in the flattening pattern, there is only one existing value, but the other 3 are zeros and so on. Yeah. So now what do you do further with this? So given a codebook pattern, only some codebooks are present at each pattern step PS, right? So at each sequence step, there is only some codebooks are present. So if the codebook is present, you essentially use a learned embedding table with n entries and d dimensions, right? So now the idea is that for every code, you're basically going to learn some embedding, and it could be randomly initialized and then learned over time, right? So that's that. Now, at any time point, to be able to come up with a representation for this time point or for the sequence step, right? You're going to add up the representations of all of those values that exist. So, for example, in the parallel pattern case, I'll basically take these four guys and then look up the code book for or look up the embedding for each of them. And essentially, I'm going to add up all of those embeddings, d-dimensional embeddings, and that would basically give me the overall representation at that sequence step. Yeah. Now, of course, I also add position information. So I'll also go ahead and add sinusoidal position embedding. Okay. Now, this is going to be passed, of course, to a transformer decoder. So remember uh, at inference time, I'm basically going to generate audio. So essentially, but this audio is going to be conditioned on the text as well. So therefore, I'll have some conditioning signal also, right? So the way my overall architecture of MusicGen is that, well, it's basically a transformer decoder, which basically takes, conditioning information. Now, this conditioning information could be an audio prompt, or it could be a text caption, as I showed to you on the first slide, right? So and then this conditioning information is sort of passed as input to this transformer decoder. So, which basically consists of self-attention block, and then the conditioning information goes to the cross-attention block. If the conditioning information is melody, so it could be text or melody. If the conditioning information is just melody, then you may not give it like cross-attention. You may actually just use it as a prefix to the transformer input. Yeah. But then if the conditioning information is text, basically you take your audio part, you give it to the self-attention block, you take your text part, give it to the cross-attention block, and then you also have, of course, your fully connected feed-forward sublayer, and then you have the linear mapping and the residual skip connections around all of these, and layer normalization and so on. Okay. So majorly, the major architecture of MusicGen is basically a transformer decoder, which mainly consists of the typical self-attention and the feed forward, but also the cross-attention sublayer, so as to take care of the conditioning information coming from the text side. Okay. So that's that. Now, in this paper, they basically train three sizes of different models. So essentially, a 300 million parameter model, 1.5 billion parameter model, and 3.3 billion parameter model. Okay. Now, what happens at the generation step, right? So essentially, this is the input, and yes, there are self-attention layers, and then at the last layer of the transformer decoder, you want to basically start predicting stuff. Okay. Now, at every sequence time step, you want to basically come up with outputs, output logics for that matter. Okay. So from the transformer decoder at every pattern time step PS, you basically want to get the logics for PS plus 1. Okay. Now, if a codebook is present, so remember it has to be a vector prediction, right? So, if a codebook is present, of course, depending on the pattern, a codebook may or may not be present for, in this vector of size 4, codebook may or may not be present. If the codebook is present, then the logic prediction is actually obtained by applying a codebook specific linear layer from D channels to N channel. Remember, the transformer decoder is acting in a space of T dimensions. So at any time step, once your transformer decoder has generated some D-dimensional representation at that time step, well, you actually project it to using four different linear layers to an output. And essentially, if you're using parallel pattern, for example, you may actually want to use all four. But if you're using a flattening pattern, then sometimes you want to use the first one, sometimes the second one, sometimes the third one, sometimes the fourth one, and so on. So it's to basically generate the discrete codes. And of course, you're going to basically use the audio decoder so as to take those discrete codes and essentially start generating the real audio waveform. Okay. Now, conditioning part, yes, as we discussed in the first slide, you could have text conditioning. You could basically say, that I want to generate a 90s rock song with a guitar riff, and in which case, basically, that's text conditioning. So you take the text and you have to encode the text as well. They basically try in this paper encoding text using three different kinds of models: T5, FLAN T5, and CLAP. So FLAN T5 is the instruction fine-tuned version of T5. CLAP is basically, joint audio text model, right? Joint audio text large language model. So before conditioning on the text, they basically do several text preprocessing steps. So for example, they remove stop words and lematize the text as text normalization step. They also concatenate extra annotation tags. This is basically for training purpose, right? So at train time, you actually have audio text aligned data. And to be able to train nicely, you remove stop words, lematize. You also concatenate annotation tags such as music key, tempo, type of instruments, etc. to the text. And then, to do good augmentation, text augmentation, you actually also do word dropout. And this augmentation is required because overall audio text aligned data is not in plenty. Okay. You could also do melody conditioning. So basically supply a small humming sound or something like that, some melodic structure, basically even whistling or humming, something like that. And you want to generate music which aligns with that input melody as well, right? So in that case, the way you input melody is to basically compute a chromogram out of it, and then you take the dominant time frequency bin in each time step and give that as extra conditioning input to your transformer decoder. Okay, so now that we already talked about MusicGen architecture, how does MusicGen perform? Okay. So in this particular paper, they basically observe that they get the best results using delay interleaving pattern. Remember, we talked about 4 different interleaving patterns: flattening, parallel, volley, and delay. They basically observe best results in delay interleaving pattern, which basically means for a 30-second audio, you have like about 1500 steps in the sequence. Okay. They trained the model with 20,000 hours of licensed music. And then the evaluation, as you see here, is actually performed by comparing across 4 different interesting baselines. And you see these 3 different models. So there are models of size 1.5 billion and 3.3 billion as well. And there are models where melody was basically where only text was given as conditioning input. And the last one basically is the one where you have the melody and text both given as the conditioning input. Okay. Now, the accuracy is sort of measured over MusicCap's test set. It's a data set of about 5,500 K samples, 10-second long each, right? And it's computed using 5 different metrics. 3 of them are automated metrics, 2 of them are human-generated metrics. So this is basically freshet audio distance, scale divergence, clap score, and then human-generated metrics are about overall quality and relevance to the text input text, right? Um, and what you observe is basically, that of course, MusicGen actually performs way better compared to existing baselines. So whatever is the metric that you care for, of course, KL divergence and these 2 metrics, lower the better. So noise to music does really very good here. But if you really look at human scores, human quality scores, you basically observe that MusicGen does better compared to existing baselines, especially on the human perception scores. Okay. Now, for melody evaluation, what they did was to essentially, evaluate how does the model perform, especially when you train on text and test also on text, but you train on text plus chroma, I mean text plus melody that is, and test only on text. Train on text plus melody and test also on text plus melody. So of course, what you see here, and again, they sort of measure the quality in terms of similarity. So this is cosine similarity between the reference and the generated melody. And then there are other measures as well. So for example, there are subjective metrics, including the overall quality, relevance to the input text, and then MEL, which is essentially alignment with the input melody as well, right? So, and what you observe is that in general, of course, text plus chroma, training the model on melody plus text as the conditioning information gives you the best results. However, what you also observe is that if you basically just trained on text, if you just basically trained on text and at test time, if you just trained on text, or other, if you train on text plus chroma, but then you just supply text at the test time, you don't do that bad. So at test time, it's okay to actually miss on the melody input, but at train time, the melody input does matter a lot in terms of overall quality of the generated audio. Okay. So that's that. Now they did other, and here are results, scaling results. Essentially, of course, they build 3 different kinds of models, and here there's nothing new. Basically, it's expected that the largest model gives you the best results. Largest model essentially leads to the best results of the generated output. Okay, so in summary, in this video, I talked about MusicGen, which is essentially a large language model to generate music conditioning on text or even input melody, right? It basically comprises of several interesting pieces in the architecture. The first one is EnCodec, which is basically autoencoder. convolutional autoencoder. Then you have residual vector quantization. You have codebook projection and positional embedding also being added. Then you have transformer decoder, which essentially tries to take in both text and melody conditioning inputs using cross-attention layers. At the output, of course, the transformer decoder does logic predictions for those code books which need to be present at any time step, at any sequence time step, right? So if you want to play around with this, music samples, chord models are all available in the audio craft library by Facebook on GitHub. That's it. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.